So what we want to do here is just solve for T final. We want to figure out what's the final temperature of this system from the setup already provided. Of course, the problem here is T final, the variable we're looking for, shows up twice in the equation. So how can we start figuring out T final if it shows up twice? What would be the algebra behind that? Yeah, I would start by combining like terms. Simplify everything you can, combine like terms. Let's go ahead and multiply these out. And with numbers like this, you may as well use a calculator. So 0.025 times 334 would be 8.35. And we can also simplify the units. Kilograms and kilograms cancel out. Plus, and then 0.025 times 4.18 would be 0.1045, and that gets distributed to both of these terms. So 0.1045 times T final. Also, what would the units be on this so far if we just multiply these together? Yeah, what we're trying to solve for here is the final temperature at thermal equilibrium. Yeah, the kilograms cancel out, so we're left with kilojoules per Kelvin times T final minus this times 0, which is just going to be 0. And we should probably rewrite kelvins as degrees Celsius here, just to be consistent. And as long as you're talking about delta, there's no difference. If you're talking about temperature on its own, that has to be in kelvins. But if you're using an equation with a delta temperature in it, Celsius and Kelvin are interchangeable as long as you're consistent about it. Because how do you convert Celsius to Kelvin? Yeah, you'd have to add 273. But if you're adding 273 to both of these, add 273 to this one, add 273 to this one, what's going to happen to those 273s when you subtract? Yeah, it's going to be the same anyway. If you had a plus 273 to this and a plus 273 to this, when you subtract those 273s, you cancel out anyway. So as long as you're talking about a delta temperature, subtracting final minus initial, it does not matter whether you're talking about Celsius or Kelvin, as long as you're consistent about it. You wouldn't want to write one of them in Kelvin and the other one in Celsius, for instance. Just make sure it's the same. But since we're talking about Celsius here, 0 times anything is still going to be 0. And then 0.25 times 3.89 will be a little less than 1, 0.9725. So 0.9725 times T final. And that's also kilojoules per degree Celsius. That's kilograms canceled out. And also that same 0.9725 times negative 95, which will be negative 92.3875. And in that case, we're canceling out the degrees Celsius and canceling out the kilograms, so we're left with kilojoules. Equals 0. And at this point, we can now combine like terms. Before we do, any questions on the simplifying so far? So combining like terms, what can we combine together here? If we just got this number plus this number times T final plus this number times T final minus this number. Yeah, anything with a times T final, those can be combined. You can even think of this as factoring out T final. So this one and this one, we can just add together the 0.1045 plus 9.725. 0.9725. So 1.077. And that keeps the units, kilojoules per degree Celsius. the other two terms are just raw numbers with no variables multiplied by them. They're both also in kilojoules. It's important that they're the same units. You can't add quantities together if they're different units. So this one minus this one, so 8.35 minus 92.3875 is negative 84.0375 kilojoules. And there's not usually all that much point to keeping that many decimal places. It's usually a good idea for a while anyway, but the final answer should probably be rounded off. So what else do we still need to do to isolate T final?
Divide the 84 by 1.077.
Yeah, we've got a minus 84.0375, so we want to add that to both sides. So we'll add 84.0375 kilojoules to both sides. Same operation both sides of the equation. So 1.077 kilojoules per degree Celsius times T final equals positive 84.0375 kilojoules. And then what? Yeah, and next we want to divide by that 1.077. And I would include the units there. We're dividing by 1.077 kilojoules per degree Celsius. So 84.0375 divided by 1.077 is about 78. And there's a lot more decimal places listed on the calculator, but we don't really want to claim more accuracy than we really have. In the original problem, it looked like everything had 3 significant figures. So I would just run this off to 78.0. Maybe 78.03 if you want to make it look more accurate. But again, you don't want to claim more accuracy than you really have. So 78, and what would the units be there? What happens when we take kilojoules and divide by kilojoules per degree Celsius? Yeah, we're left with just degrees Celsius. Because remember, dividing by a fraction is the same as multiplying by its denominator, or multiplying by its reciprocal. Dividing by kilojoules per degree Celsius is the same as multiplying by degrees Celsius per kilojoule. Kilojoules cancel out, we're left with degrees Celsius in the denominator. So that's what the final temperature should be, 78 degrees. And yeah, not sure why the answer key would say 82.5. It looks like this boils down to 78 degrees after all. Any other questions on that one? And yeah, I'm pretty sure that is 78 degrees. I'm not seeing how that could be anything else. And generally, physics is going to involve a lot of algebra. There's lots of situations where you have some big complicated equation and you're trying to figure out what's the value of this one thing from it. So make sure you get plenty of practice with that. If you're stuck, try just writing out every step. A lot of times solution guides or instructors will skip steps, like write out, this is true, therefore clearly this is true. But always be willing to write out the extra steps if you need to. Write as many extra steps in between as you need to make it make sense to you. Or if you're comfortable with it, skip some steps, just make sure you know what you're doing and you know what's happening in the steps you skip. But if you're not sure, write it all out. Any other questions on the algebra there? And again, if you want some more practice on the thermal energy and bond stuff, take a look at the worksheet on math.andcheese.org/P7A. And feel free to bring that into office hours or ask me on the Discord if you have any questions about that. Beyond that, let's take a look at the mechanical energies, kinetic energies and potential energies. all this stuff about conservation of energy ultimately goes back to an idea that the 7 series doesn't really cover in detail until 7B. But I think it's a good idea to take a quick look at this idea of force before we get into mechanical energy in much detail. The 7 series covers material, most of the same material that a traditional physics class would, but in a different order. And most of the changes in order, I think, are a good idea, except they usually don't talk much about force until 7B. But force is very important for understanding what energy really is. And what do we mean by a force? If you're applying a force to an object, what does that mean? What is a force? It's related to energy, and it's certainly a type of action. A force is an action word, almost like a verb. Well, applying a force would be the verb. But yeah, you could think of it as a push or a pull. If you just have, like, let's say a box and you push on it, you're applying a force. Or if you lift something up, you're applying a force. Or if you grab a rope and pull, you're applying a force. And other forces exist in nature as well, like force of gravity, for instance, just the force pulling something down. Force of gravity is a force. Magnetic attraction and repulsion would be a force. Electric attraction and repulsion is a force. Even just like holding something still, I'm applying a force to this marker to prevent it from falling. So any push or pull, and specifically, what does that cause? If you've got a moving object and you push on it, what happens to that moving object? Like, let's say there's just this cart rolling by. Well, what if it's already moving? I mean, if it's not moving and you push on it, you could make it start moving. But what if the object's already in motion and you push on it? Yeah, maybe you make it move faster. Or if it's moving in one direction and you push it the other direction, what do you cause it to happen? Yeah, you might make it slow down. Or even if it's moving in one direction and you push it sideways, you might make it change direction of travel. Either way, forces can cause a change to velocity, change to the motion of the object. And what do we call the rate at which the velocity changes? How fast the velocity is changing? What do we call, well, speed is how fast the object is moving. What would you call how fast the speed is changing? Because when force is involved, it's not really important how fast it's moving. What's important is how fast its motion is changing. Yeah, acceleration. Acceleration means how fast the velocity is changing. And that's what a force does. Specifically, acceleration is the rate of change in velocity. Change in velocity over change in time. And like many things in physics, it's defined as a derivative, a rate of change. How much the velocity changes divided by how much the time changes. And they're proportional. Force is proportional to acceleration in the sense that if you want an object to accelerate at a certain rate, if you want its speed to change at a certain rate of change, you have to apply a certain amount of force. If you want it to accelerate at, let's say, 10 times that rate, if you want its speed to change 10 times as much in the same amount of time, you have to apply 10 times as much force. And that means we can write it as an equation. If two quantities are proportional, what does that mean about them in terms of an equation? One of them has to equal some constant times the other one. If we say force is proportional to acceleration, then force has to equal some constant times acceleration. And what do you think that constant is? What property of the object is going to determine how much force you need to make it accelerate at a certain rate? This ends up being the mass of the object. Because the more massive the object is, the more force is needed to make it accelerate at a certain rate. And of course, any total force will make it accelerate. Even if you've got an object floating in space that's very massive and you apply only a tiny bit of force, you are causing acceleration. It's just that a large mass and a small force will lead to a very small acceleration. But the more massive it is, the more force is needed to make it accelerate at a certain rate. Like if you've got two objects and you want them both to accelerate at the same rate, the more massive one needs more force to make it keep up. So you could think of mass as being like a difficulty level. It's tempting to think of mass as how much stuff there is in the object. But the best way to think of mass in terms of physics of motion is how difficult it is to change the motion of the object. More massive means it's more difficult to change the object's motion. Any questions on that so far? So the way this all ties into energy, if you want to change the energy of an object, you can do what to it? What do you have to do to an object? What do you have to apply to an object to change its energy, like to add energy to it? Yeah, heat or work. Heat, usually written as Q. Heat is a transfer of energy caused by what? What has to be happening to make heat flow? Or what does heat flow from and what does heat flow to? Yeah, there's got to be some difference in temperature. And specifically, heat is going to flow from where to where? Yeah, from the high temperature zone or object towards the low temperature zone or object. Heat flow is caused by this difference in temperature, not from time to time, but from location to location. If two locations nearby are at different temperatures, heat is going to flow from high temperature to low temperature. And also, the more different these temperatures are, the faster heat is going to flow. We're not going to look into how fast heat flows in much detail in 7A. We're going to look at it briefly in 7B. But the main idea is the more different the temperatures are, the faster heat is going to flow. So that's one way of transferring energy. Or you could transfer energy mechanically as work. So work, what has to be happening in order for an energy transfer to count as work? What is work? For instance, if I take a heavy box, yeah, it's got to be a transfer of energy related to some sort of force. It doesn't necessarily have to be total force. You could be applying a force to the object while some other forces are also acting on it. But if you, like, let's say you're holding a box and you're lifting it. You're applying an upward force because you're counteracting one other force. If you are, even if you're just holding the box in place, yeah, you're acting against gravity. The forces on this box would be, you've got gravity pulling it down, but you've also got your own hands pushing it up. So you've got a force of gravity pulling down and a force from your hands pushing up. In order to keep this in motion at a constant speed, you'd have to have the force from your hands balancing out the force of gravity precisely. If you applied more force, then the total force wouldn't be zero, so the object would accelerate. If you want no acceleration, if you want the box to either stay still or be moving at a constant rate, you need the total force to be zero, which means the force from your hands has to balance out the force of gravity. So that's one of the important principles here. If the object is moving at a constant rate or staying still, the applied force has to be the exact opposite of, in this case, the force of gravity, but in general, whatever other force is acting on it. And we denote that opposite direction with a negative sign. Negative sign here just means in the opposite direction. So this is just saying the force you're applying is the exact opposite of whatever other force is trying to make you accelerate in a direction you don't want. Any questions on force so far? And then this idea of work. If you're just holding an object in place, you're applying a force to it to prevent it from falling. Does that count as doing work? Or if I'm leaning on the wall here, I'm applying a force to the wall. Am I doing work to the wall? If I'm just pushing on the wall but nothing happens, we probably don't want to classify that as work, right? To count as work, you need to be applying a force to the object, and also what else has to be happening. It's got to be changing, specifically changing its position. To count as work, you've got to be applying a force to the object, and the object has to be in motion. So if you're just holding the box still, that doesn't count as doing work. But if you're lifting the box, if you're pushing up on the box while it moves up, or even if you're lowering it, if you're pushing up while it lowers down, that also counts as work. So work involves a force acting on a moving object. So we can define work in that way. Work is energy transfer caused by a force on a moving object. And also part of the definition there is that the force can't be perpendicular to the object. For instance, if you've got an object that's moving horizontally and you're pushing down on it, your force is perpendicular to the motion. So that doesn't actually count as work. But if it's moving horizontally and you're pushing diagonally, at least some of your push is in the same direction it's moving. So that still counts as work. And we'll get into that idea of directionality more in 7b. But for now, let's just assume everything is one-dimensional motion, just moving along a straight line. We can actually calculate work as well by just multiplying force times distance. Usually written as F times delta X. So this is usually how we calculate work. If you're applying a force to a moving object, you can multiply how much force you're applying times how much distance the object travels. And that product will tell you how much work is done. Any questions on that so far? And while we're at it, let's also take a look at how the units of measurement play into this. Since we've got all these equations up on the board, let's start with velocity. Anyone know what units velocity is measured in? The variables, yeah, let's go through the variables as we look at the units of measurement. Velocity describing the how fast the object is moving. Yeah, F is force. And X, we're using X to represent position here. So delta X is distance traveled. So force times distance traveled. And what do we usually measure distance in? Yeah, distance is going to be measured in meters. And anyone know what the unit of measurement for force is? Yeah, force we usually measure in newtons. Newton is written as a capital N. And work is a transfer of energy. So what do the units of work have to be? Yeah, kilojoules, or let's just say joules. And so in order for this to make any sense, these have to equal each other. Joules has to equal newtons times meters. And it does. This is part of the way they're defined. Joules can be rewritten as newtons times meters, or newtons times meters can be rewritten as joules. You can even think of joules as just an abbreviation for Newton meters. And that's even true for joules no matter what type of energy it's measured. Even all of the thermal energy and bond energy stuff, all of those joules could be replaced with newtons times meters. There's usually not much reason to, but you certainly could make that substitution. And if we go back to the definition of force in the first place, force has got to be measured in newtons. But what's mass measured in? Yeah, grams or kilograms. Usually we use kilograms in this context. And as for acceleration, if we go back to how that was defined, change in speed over change in time, what's speed usually measured in? How would you describe the speed of an object? What units of measurement would you use there? Yeah, meters per second. So change in velocity would be in meters per second, and time, of course, would be in seconds. So if you take meters per second and divide by seconds, what would you get? What happens to those seconds? Yeah, those are going to combine because you've got seconds in the denominator, and by dividing, you're putting another seconds in the denominator. So you get meters per second squared. So that would be the units of measurement for acceleration. For instance, if your acceleration is, let's say, 5 meters per second squared, that also sometimes read as meters per second per second. 5 meters per second just means your speed is changing by 5 meters per second every second. And if we fill that in here, we actually get the meaning of newtons. Newtons can be broken down into these more basic units. Kilograms, meters, and seconds are the most basic fundamental units. Everything else can be written in terms of those. Well, those, and also coulombs, the unit of charge, which we'll get to in 7b. But until we get to electrical stuff, every unit of measurement can be written in terms of kilograms, meters, and seconds. Newtons, for instance, is kilograms meters per second squared. In the sense that anytime we write newtons, we're really just using that as an abbreviation for kilogram meters per second squared. And also we could fill that in here. Newtons is kilogram meters per second squared. To change that to joules, we would just multiply by meters again. Meters times an extra meters would be meters squared. So joules can be written as kilograms times meters squared over seconds squared. So all of these more complicated units of measurement can be written as some sort of combination of the basic units, kilograms, meters, and seconds. Any questions on those so far? All right, then let's see how it goes into energy again. If we start with this idea of work, like let's say you're applying a force to an object, you're doing some work, force times distance. That is work. But you are, and let's say this is your applied force. But we know force is equal to mass times acceleration, so we can make this substitution. Force can be written as mass times acceleration times delta x. Just making the substitution. But also, what is acceleration equal to? Acceleration is equal to force over mass, but that'll just put us back to where we started. How are we defining acceleration in the first place?
Change in velocity over change in time.
Yeah, acceleration is just change in velocity over change in time. So we can substitute that in for acceleration as well and get mass times change in velocity over change in time times delta x. Also, going back to the equation in blue, yeah, this is saying the applied force, like let's say you're lifting an object. The force you're applying times the distance the object travels, equals the mass of the object times the acceleration of the object, since force is mass times acceleration, times the distance traveled. And if we rearrange this a little bit, what do we call distance over time? What is that the definition of? Yeah, that itself is velocity. Distance over time is velocity. And if we fill in the rest, we've still got times mass We still got a times delta velocity. And that should equal applied force times distance. The thing is, though, if we're talking about a force that might be changing as time passes, the idea that work is force times distance doesn't really hold up. Because if force is changing, you need to know what force you're using, the starting force or the ending force or somewhere in between. So what we often do is split this up into much smaller pieces of distance. Let's say you've got an object that's traveling and you're changing the force you're applying to it. You apply maybe a large force to start with for a short amount of distance, then a weaker force for a short amount of distance, and so on. So instead of taking one force times the whole distance, we can take the force right now times a tiny bit of distance, plus the force a little later times the next little bit of distance, plus the next bit of force times the next bit of distance, and so on. So we'd be adding together all the little bits of force times distance, and also adding together all the little bits of mass times velocity times change in velocity to get the total amount of work. But if we make those changes small enough, if we look at a bunch of little tiny pieces added together, where have you seen that before in calculus? The idea of taking a bunch of little tiny pieces added together to get a more exact value. If you're adding together more and more little tiny pieces to get the total amount that has built up, yeah, this is ultimately an integral. This idea of adding together some function times a little tiny change in x, that's ultimately building up to the idea of an integral. That if we just use some big chunk of x, we're going to get an approximation. But if we make the pieces of x smaller and smaller, we're looking at an integral to get the exact value. And this might make more sense if you look at a graph of x versus force. Like, let's say the force is changing at different locations. If you multiply some amount of distance times some amount of force, you're going to get an area under the curve. But if you make those rectangles smaller and smaller and smaller, smaller rectangles allows you to get a better approximation of the curve. So if we make these rectangles small enough, instead of a summation, we would write this as an integral sign. And instead of delta x, we would write this as dx. Likewise over here, instead of writing a summation, we write it as an integral sign. And instead of delta v, we write it as dv. And here's something we can actually integrate. M is a constant, but we're integrating v with respect to v. And we can pull out. Anyone remember what the integral of v with respect to v would be? Yeah, that ends up being v squared, because this is v to the first. When you take the integral, you'd add 1 to the exponent and then divide by the new exponent, so v squared over 2. So that means the amount of work you did to the object equals this amount, mv squared over 2. In the sense that you're applying work to make the object get faster and faster and faster. And the amount of work you've done is mv squared over 2. But work is ultimately a transfer of what? When you do work to an object, yeah, you're transferring energy. So that means what we ended up with the work equaling is an amount of energy. This is a form of energy associated with speed. So what do we call that? What we call a type of energy associated with how fast the object is moving. Power isn't actually a type of energy. Power is the rate of transfer of energy. Power is how much energy per second. So it's the rate at which energy is being delivered. But if this is an energy associated with motion, we usually call this kinetic energy. Yeah, exactly, kinetic. Or KE. Kinetic just means having to do with motion. Same root word as cinema, moving pictures. So this is a formula we can use for how much energy the object has because it is in motion. Like if you imagine you have an object that starts off at rest, you apply a force to get it moving faster and faster and faster. This is how much work you did to the object to make it move at that speed in the first place. Or alternatively, how much work you'd have to do in the other direction to bring it to a stop. So this is the energy the object has because of its motion, and we call that kinetic energy. Any questions on that so far? And also, if you take a look at the units, what's mass typically measured in? Kilograms. And then speed would be measured in meters per second. But we're squaring that, so we get meters squared over seconds squared. And kilograms meters squared over seconds squared is the exact definition of joules. So this works out to exactly what we need for the units measurement anyway. Kilograms times meters squared over seconds squared becomes joules. Any questions on that idea of kinetic energy so far? Then let's try out a quick numerical example of that. Let's say you are throwing a bowling ball. You've got this bowling ball in your hand, you reach back and you throw. So before, you have the bowling ball at rest behind you. After, you have just let go of the bowling ball and it's now going at some fast speed. So V initial was 0. And V final, let's say you want this bowling ball to be moving at, let's say, 20 meters per second. That might be a little faster than realistic for a bowling ball. It's about 40 miles an hour. It's probably pretty fast. Let's say 15 meters per second. How are you making it go fast in the first place? What are you doing to the bowling ball to make it go fast? Yeah, you're applying a force, and more specifically, you're applying a force while it is doing what? To count as work, you've got to apply a force, yeah, exactly, while it's in motion. So you are doing work. You're changing the kinetic energy of the object by doing work to it. We can even draw this out as an energy interaction diagram. You have the kinetic energy of the object increasing because its speed is increasing. And we usually write speed in absolute value because the positive or negative sign refers to direction. We don't care which direction it's moving, we just care that it's getting faster. We know its initial speed, 0. We know its final speed, 15 meters per second. That's the only thing that's changing. So we treat this as an open system with work being done to it, work entering the system. So what would our conservation of energy equation look like then? We definitely have a change in kinetic energy. What can we say about that change in kinetic energy in terms of an equation? It should definitely be positive. because we're increasing the kinetic energy. But what should it be equal to? What would our conservation of energy equation look like here? We've got just kinetic energy changing on one side of the equation because there's no other types of energy involved. But what's causing that? Yeah, delta kinetic energy equals work. Because we can always start with delta E total equals work plus heat. The only type of energy changing is kinetic energy, and there's no heat, so it's just work. And for change in kinetic energy is 1/2 mv squared, or mv squared over 2. But of that, what's the only part that's actually changing? As you shove the ball, what's the only piece of this that changes? Yeah, velocity. So delta kinetic energy, if you think of this as 1/2 mv final squared minus 1/2 mv initial squared, because we're taking final minus initial. Since the mass and the divided by 2 are the same, we can factor that out. And we're left with v final squared minus v initial squared. Or usually written as m over 2 times delta and then v squared in parentheses. The v squared being in parentheses should be a reminder that you're squaring both of the velocities first and then subtracting. You're not subtracting final minus initial and then squaring the result. You are squaring the final velocity and squaring the initial velocity separately, and then subtracting those squared velocities. So if we write that out, we've got m over 2 times v final squared minus v initial squared. And also, what could we replace work with? How are we defining work in the first place here? That was just force times distance, right? So we could replace work with force times distance. Assuming you're talking about just a single constant amount of force from your hand, that means if you know the starting and ending speed of the bowling ball from 0 to 15 meters per second, and if you also know the mass, and you know how far it is from where it started to where it ended, what could you then solve for? What else would still be unknown here? For instance, let's say we know that from the initial location of the ball to the final location of the ball, let's say that's maybe 2 meters. So that would be delta x. So let's say that's already known. You know where the ball started and you know where you let go of it. And let's say we also know the mass. The bowling ball usually has its weight listed on the side. So let's say we know its mass is maybe, I don't know, 10 kilograms. At that point, what would be the only unknown left? Yeah, the force. If you know how far your arm swings when you throw it, that is from the starting location of the ball to the ending location of the ball, and you know how fast it's going at the end, and then it started at rest, and you know how massive the object is, you can solve for force. That tells you how much force you had to exert on the ball while throwing. Or alternatively, if you knew how much force and how much distance, you could solve, for example, for how fast it would be going when you let go. So as usual, if you've got an equation with a whole bunch of unknowns, as long as you know all but one of those values, you can solve for that last unknown. Any other questions on that so far? So that's kinetic energy, the energy associated with changes in speed. Change in kinetic energy is always going to be half the mass times change in squared speed. We can generally think of absolute value of speed as the indicator. The sign, positive or negative sign, doesn't matter because we're going to be squaring it anyway. All that matters is it getting faster or slower? Potential energy is more the energy associated with position and some type of force. For instance, there's the potential energy associated with gravitational force, potential energy associated with the force of the spring, and various others. So we'll look into potential energy of gravity and presumably springs next time. Feel free to email me or let me know on Discord if you have any other questions, and I will see you then. Okay.